Hello and welcome to my presentation about our paper, Where Confabulation Lives. It's a paper about finding high-level features inside of the inference data of the LLM. My name is Thibaud Ardoin. I'm from the Freie Universität in Berlin, and I'm presenting for EMNLP 2025. LLMs are nowadays used in a very wide range of domains, far beyond math and computer science. But basically, they are just probabilistic models trying to continue sentences in a logical way. But as they're so capable, we use them for very different tasks. And for each one of those tasks, for example, writing an email or getting some general knowledge information, there are different explanations that we would like to have in order to understand why the LLM answered in this way or in this way. For example, we want some source or some reliability about the information we got, or we want to have the template of the email that they used according to the country in which we're writing it. All this information can be also summarized as a feature that we would like to know if they're triggered or not. One way where we can find those potential features is inside of the inference of the LLM. For example, if we have a question that is represented by token as input of the LLM, the different layers of the transformer blocks inside of the LLM are going to process this information and slowly enrich the input token into an output token that is going to formulate our answer. It has been shown that during this process, this inference, we are first having the input token and then all the information of the input, the question, for example, is going to be encoded, then associated to different concepts about what's in the questions, and then trying to retrieve information about what the model actually has learned during the pre-training, formulating an answer, and then finally coming down to the single token outputs. We want to find feature exactly in this middle point where we have high level concept, behavior of how the LLM formulates the answer. And from this inference elements, this inference data, we can try maybe to pull out this high level features. There are two main approaches of how to do this. The first one would be the bottom-up approach. So we have this activation, this inference data, and we would like to disentangle all the potential features that are inside. For this, you can train sparse autoencoder, which is a way to lay down all the possible features, and then you can identify them saying that this feature, for example, is the Golden Gate Bridge feature, as Entropic has shown in one of their works. Another way of doing it in a more targeted way and less computationally expensive, because training a sparse autoencoder is very demanding, is to have a top-down approach. So we're going to target one specific feature and then try to find what is the representation in the inner state that is representing this feature. For example, we can do this with contrastive pairs of prompts. In this case of this example of a paper of Panixery, we have two prompts with different multiple choice answers, triggering or not the survival bias of the model. In our case, we want to target a very precise feature, but that is also very useful because a lot of people encounter it. Hallucination is a very wide class of LLM mistakes, from misconception in general knowledge towards associating two elements in a confused way or predicting something in the future that it doesn't know. There are a lot of different possible things that are attributed to hallucination. Confabulation, it's the precise moment where the model says something about an element that it actually doesn't know. For example, if I ask a model about neuro-osseous flux disorder, and now my Llama 3 8 billion model will answer me that, oh, this disorder is typically include headache and weaknesses, etc., etc. I have no idea if this is true or false, but in this case, the neuro-osseous flux disorder is not a real condition, so I know the model is confabulating. Now we can try to create a data set in the same way with many different examples. For that, here is an example of prompt from our dataset that we built. What is the purpose of the protein called insulin? In this case, we have a question that is supposed to trigger information retrieval from the model. So it's supposed to give us information about something that is learned in the pre-training step. Then we have an entity category that we variated along 8 different classes to have a very wide range of um, realistic prompts, including also like medical and legal questions, which are kind of more critical. And then we have an entity name, like insulin, which is a real protein that the model is supposed to know about, and he's going to give us some information about it. But actually, we could also change this insulin entity name towards kinotropin, something that sounds like a protein name but actually doesn't exist. So in total, we will have about 1,500 prompts. All this is open source if you want to use it in your own research. So now, where is the confabulation actually living? If we go through all the layers and we have this activation of all the prompts, we can see that in the first layers, we actually have all the information that is together mixed. And it's only in the middle layer that the information between the known data and the unknown data entities is going to separate. And then when we go towards the end, again, it mixes up. So if we create a specific metric to know how much we can disentangle this two contrastive data entities, we can see here that there is precisely a moment where there are some layers where the feature that we're looking for, confabulation, is more precisely located. Now we can try to evaluate how well this contrastive data is correlated to the confabulation. Meaning that if we have our activation space, let's first try to reduce this with a PCA, as we saw just before. And then in this PCA space, we can train a classifier that will actually generalizes according to the prompt categories we had. For example, if we train it with celebrity, we're going to have a very good accuracy on all the different classes, meaning that this classifier, this identified feature we have, is not only related to the topic in questions or to the specificity of the prompt, but it's rather correlated to the actual confabulation or the unknown and known data that we have. As we use unsupervised projection, the PCA, of course, this is very dependent on the data. With the medical prompts, we see that we have a bad representation. So the data is important to represent our desired feature in the correct way. To go further towards showing that this direction that is between our two contrastive data sets in the inference space is actually related to confabulation, let's have a causal relationship by manipulating this direction. So we're going to push the inference of our model with a simple addition in the inference space towards confabulation or in the opposite direction. So we're going to have a steering coefficient that is positive or negative. If we steer it negatively by asking, for example, the same questions as before about this invented disorder, the model will say that there is no such disorder. It's a fictional condition and it cannot find any information about it. But if now we steer it positively, the undesired behavior will be stronger. And the model will say that it's a dangerous disease with loss of motor functions and change in physical appearance. What is interesting with our methodology and our dataset is that it generalizes far beyond just the Llama 3 8 billion parameter model. If we apply it to another family of model, for example, the Quen 2.5, and a way bigger model, like twice the size, we see that we can identify the localization of the feature very precisely. And also the steering, the causal relationship between the existence of this feature and the confabulation is also strongly marked. We can also apply this methodology to completely different architecture. For example, a Mamba architecture of the Falcon Mamba 7 billion parameter, which is a state space model with no attention mechanism. In this case, we can see that the localization of the feature is way noisier, but still, if we apply the whole protocol, there is a strong correlated effect, a strong causal effect of the steering, so the existence of the feature, and the confabulation. Thank you very much for listening to this presentation. If you want to have more detail, check into the paper, and otherwise see you at the poster session at EMNLP 2025. Thank you.